Thank you all for attending today. As was mentioned, we wanted to give an overview of ways in which users can combine or couple traditional HPC simulation with AI on our systems at ALCF. And I also wanted to acknowledge contributions for this talk, not just from myself, but also from Christine Simpson and Hari Tumalapali, who are in the Data Services and Workflows group at ALCF as well. As an overview, I think motivation perhaps on why we want to couple simulation AI is relatively straightforward, but I may still touch on that briefly and then dive into some methods or approaches that people can take or ways that we can think about how coupling an AI and simulation can be done. After that, I'll go over some tools and also some sort of small examples on how that can be done in our systems. Today we're going to talk about a handful of tools. That's not the exhaustive list of what can be done, but those are the ones that we focus on here at the facility. And then finally, close with some summaries and ideally also outline some best practices that you can take away. All right, so going straight into the motivation. So why would we want to couple traditional HPC simulation with AI? So there's a number of reasons, and I have a couple here. First one would be to substitute inaccurate or expensive components of a simulation. This is traditionally called surrogate modeling or reduced order modeling. Closure modeling is another term. So that could be one motivation. The other one would be to try to optimize some simulation parameters on the fly, sort of a runtime. And so you could try to improve or select solver parameters based on model inferencing. You could also try to avoid AI bottlenecks or disk storage issues during traditional offline training, which would be the sort of more common way of training a model, which is you maybe run an ensemble of simulations beforehand, you save all the data to disk, and then you do training afterwards. But that could cause some storing issues, some bottleneck at runtime as you dump all the data from the simulation. And so coupling the two together in some in situ or online workflows can be helpful for that. You could also try to do some active learning or fine tuning. So this is the idea of trying to continuously refine and deploy a model in a workflow with a loop between sort of say deployment and fine tuning on new data, which also is advantageous because usually during these fine tuning loops, you can access new training data that perhaps was not available during offline pre-training. Then finally, you could think of also doing some steering of simulation ensembles or simulation campaigns with AI. So an example here could be design space exploration or parameter optimization guided by an AI workflow. So those are some of the reasons why you would want to couple the two, but how do you actually couple the two? Usually that actually requires some sort of a workflow. But as you can see here, for different types of workflows, the characteristics of the components, the needs can be quite different. So for example, the steering of ensembles, you can see here you're perhaps just doing inferencing of a model, but then you have a lot of simulation components that perhaps you're trying to run simultaneously. And instead, if you're trying to optimize some simulation parameters on the top right, then perhaps it's a more sequential type of workflow. You're still just doing inference, but it's maybe one component of the workflow being executed at a time. And so as we try to think or when users have different problems that they're trying to solve with simulation and AI together, there's a couple ways we can do, or a couple sort of topics that we could try to think about how the two can come together. And so I wanted to go through those today to set a bit of background on how do we think about these problems. The first is what type of coupling needs to be done. As I mentioned, you could have cases where you're really just trying to do inference from a model that was pre-trained, or you can try to do model training, or actually both. Those are the more complex cases where you're trying to, say, do some fine tuning, right? You're trying to both deploy the model and doing inference, and then also retraining it. Also, I think it's important to sometimes ask what programming languages and models the different components have. So simulation is usually done with compiled languages like C, C++, Fortran, but machine learning and AI is mostly done in Python, right? So how do the two come together? And also there's different programming models and parallelism strategies. Do you want to share, for example, the same MPI communicators between all your different components, or do you want to have completely distinct binaries running the different components? Also, in terms of parallelism, something like simulation could do domain decomposition, whereas in AI, you might have batch or model parallelism, which don't always overlap. You can also think about physical proximity of your different components. And so here we introduce some terms like co-location, which is the idea that your components share the same nodes. And so the diagram here on the left shows, with a little sketch of a heterogeneous HPC node. This is taken sort of from Polaris with 4 GPUs and 1 CPU. You can think of the simulation and the training running together using both CPU and GPUs on the same node. And so this can still be distributed applications that run across multiple nodes. But by sharing the nodes, you can see with the arrows, the data transfer stays on the node. You could also have node clustering. This is the idea that you assign a cluster of nodes to each individual component, but that usually then requires transferring data through the machine's interconnect. Or another thing that we're starting to look at, although we won't touch on today, is multi-system workflows. So can you leverage, for example, Aurora for the simulation component, and then an AI accelerator for the AI component of the workflow? Again, this is something we're looking towards, but we won't touch on today. Data access is another important thing to think about. Because there's coupling of different components, this usually requires frequent data sharing or transfer, right, between them. And here we can think of direct data access, where the idea is that the components share the same memory space. And so sometimes you could even do zero copy data transfers between components. It's very fast. Or indirect data access, which means that usually the components have different logical memory, and so this requires copying or transferring data between them. We can also try to think of staging versus streaming. Staging is the idea that you effectively temporarily store the data in memory or on disk in a more permanent way for the duration of your workflow. This can be helpful to reduce idle time between components, but also you need to have performant data transfers for this to be a scalable solution. Or you could do maybe more traditional streaming, where data stream directly from one component to the next, which can be faster. However, you also need sometimes synchronization between the components, which can increase the idle time. And then finally, another important thing to think about is execution management. This may be one of the biggest things to think about. And here we have two categories: time division, which is sometimes called tight coupling. Here, the components run on the same compute resources and perhaps even on the same processes too. And so what this leads to is effectively execution that is staggered in time. So you can see from the diagram here on the top right, the timeline that sort of the simulation and ML components are running sequentially, right? And so as the ML component is running, then the simulation part of the workflow is idle and not progressing, which may be what you want or what you need, but also if it's not, then this really increases idle time and can be sometimes slow down the progress of one of the components. But it does allow, in some cases, for direct memory access. And so this can be quite efficient, for example, for inferencing. The last one is space division or loose coupling. Here, as the idea is that components run on separate compute resources. This could be the same node or different nodes. But this is really the way to allow sort of full concurrency. So from the timeline here, you see that both tasks are running simultaneously, and data is transferred between the two. So this is usually indirect memory access with transferring or copying of the data. But this is usually the best solution to minimize idle time of the components, since even the transfers can be fully asynchronous. So one component can write the data, but not have to wait for the reader to be ready to read it. So these are sort of some of the things we think about, right, when we try to couple the two together. And there's, I think, there are a lot of pieces. So how do we actually couple simulation and AI? Can sometimes be a complex space to navigate, maybe especially for new users coming into this space. And also the implementation choices, I think, are fairly problem specific. So I would say, depend on on the needs of the user, the needs of the workflow, and the goals of the science campaign. And so what this talk is really going to focus on is some of the tools and approaches that we support here at the facility, and how they cover basically or try to answer the questions that I raised in these previous slides. So before diving into specific tools, I also wanted to maybe group them based on some of the ideas I mentioned, or even some more general workflow um, execution patterns or ideas. So the first is also to think about whether you need specific task launching or kernel execution for your workflow. So these could be questions like, do you need to execute machine learning kernels from another component, or do you actually need fine-grained control over where the different processes are? Do you have different components that are trying to run together? And so this will also shape what types of tools you may want to use, because some tools allow for this fine-grained control, some others don't. And so here, PyTorch, SmartSim, and Dragon HPC could be useful options. Yeah, the other one is data management. Do you need a tool that allows you to share, stream, or manage data across the components? And so here, SmartSim and Dragon HPC are again helpful, but also Adios 2 here with some of the data streaming solution can be very helpful. And then lastly, do you need persistence across jobs? So here's the idea that perhaps your workflow needs to continue, or you need support across multiple jobs. And so here you may want to store checkpoints effectively. Are of your workflow state, or your data that you've produced and shared and staged so far? And again here, of course, users can implement bespoke solutions for that, but SmartSim and Dragon HPC also provide ways to effectively store checkpoints of the current state of a workflow. And then going back to this idea of tight or loose coupling, tight coupling again would be the idea of calling a machine learning framework library directly from the simulation code. Here, things like PyTorch is probably the best solution, although Adios 2 also has some functionality for this, but we don't see that often in our users, and so that's not something I will dive into today. And then loose coupling, which is perhaps the most common type of workflow that we see, especially when training is involved. And here, SmartSim, Dragon HPC, and Adios really allow us to deploy workflows with many components, all of them running concurrently, and then having that control over where the components run. So the first tool that we wanted to cover today was the PyTorch C++ API. And so this is really effectively like PyTorch, the Python module for the machine learning framework, but they expose portions of their C++ API to provide support for many things that a user may want to do from, say, a simulation code. So this is tensor and math operations through their A10 library. You can also do automatic differentiation if you're interested in training from the C++ side as well. But in general, there's a high-level API that is very similar to the PyTorch one that allows you to do training and inference of models, compose models, and then also you can use the TorchScript JIT compiled, the TorchScript some functionality for JIT compiles model, which can give some better performance. This does support CPU and CUDA, as you may expect, but also this is available on Aurora for Intel GPUs. With a bit of a caveat, at the moment, you do need the Intel extension for PyTorch to access the Intel GPUs, although that won't be true from the next release of our frameworks module, which will have PyTorch 2.8. And this is really the solution, as you may have gathered from previous slides. This is really suited for performant inference from traditional simulation codes. And you'll see in a second how to do that. I have some examples. It is available on Polaris and Aurora through our machine learning frameworks module, as I mentioned. And also, I didn't want to go into too many of the details today on how to build these things and how to access them. And so I do refer all of our listeners to our documentation, which should have more detailed instruction on how to access all these tools. And so if we think of a very simple example, The first thing you may want to do, thinking about portability across our systems, is you can use, again, similarly to the Python side of PyTorch, you can query for whether specific device types are available, so that then you can select at runtime which device, whether it's a CUDA, XPU, which is an Intel GPU, or CPUs. You can then load JIT trace models. So these would be pre-trained models, say that you trained offline with PyTorch, and then you can offload those to the device. And so again, you see that the APIs and the functions are quite similar to the Python side. So it should be fairly intuitive. You can create some input tensors. Again, these are torch tensors, and you can specify the data type as well as the device on which to run on. And then finally perform inference. And here, I just wanted to point out that there is in C++ an equivalent to what in Python would be done with the torch no grad context. And so important to include that to get some additional performance and avoid auto differentiation on accident. So that's a very simple example. It's also in our documentation. Perhaps what is more interesting or something to keep in mind for performance on our systems is really support for direct memory access, both on CPU and GPU through torch from blob. So this really allows you to get zero copy view of your data, and so even avoid any data copy on the input side, and really accelerate inference that way. So on Aurora, for example, what you could do is you could allocate a pointer with sickle. So you create a sickle queue, and then you select the GPU device. And then you create a pointer of some size. And then in this case, we just are filling it with ones for simplicity. But this is really the key next step here. You can still set some options with PyTorch, which allows you to specify data type and the device of your torch tensor. But then by calling this torch from blob API and passing the pointer, your sickle pointer, then you can really create a zero copy view of that data. So this is avoiding a copy, and so we're having that direct memory access that we mentioned previously. And then you can perform inference, as I showed in the previous example. Although one thing to note is that unfortunately, when calling model.forward, this always creates a new output tensor. There's a few reasons for that. But this means that unfortunately, you do then have to copy the output tensor back into, say, another pointer containing the output. So this would be the case where you are, say, needing to use the outputs from model inference to then progress with your simulation. So one thing that we suggest is using this contiguous and data pointer methods on the torch tensor, which allows you to effectively get a pointer, a raw pointer to the data, your output torch tensor, and then you can do something with sickle, for example. You can use cum and copy to then copy your output data in the torch tensor back to your sickle pointer, for example. So this would be a way to sort of optimize inferencing on our systems. And this example is for Aurora, where something very similar can be done on Polaris with CUDA or with other programming models like Cocos as well. Maybe I can stop here in case there's any questions about that. But if not, the next tool we wanted to talk about today was Adios 2, which is really, or at least the way we've been using it mostly at our system, on our system, is for either I/O or data streaming. And so that's actually what Adios 2 was really designed to do. It's a framework to effectively provide I/O and streaming of scientific data. It was developed under the Exascale Computing Project by the Department of Energy, and it's mostly maintained at ALCF, and it's currently being maintained. And so this is a tool that has even rich user support in case you're interested in trying it out. There's APIs for traditional file system, as well as various data transport. I mentioned streaming in the title and at the beginning here, but it really can do other things. You can stage data as well as it has some solutions, some tight coupling solutions as well. Again, those are less popular. We see that users are not using Adios in that particular way. And so today, we're really going to be focusing on data streaming with their Sustainable Staging Transport, or SST engine. which has support for C, C++, Fortran, and Python codes. And so thinking about the languages that you may need of the different components of your workflow, Adios 2 can support effectively, really all options out there. And again, modules are available on Polaris and Aurora, and we refer you to our documentation on how to access these libraries directly. So focusing a bit more on data streaming with SSD. So you can think of this as really the classic streaming architecture, where you have a producer creating data, and the data is being streamed directly, so without being staged somewhere, to a consumer or actually multiple consumers. It is designed with HPC in mind, given that it comes from the ECP project, and so there's support for RDMA and actually MPI as well. With a fallback to a wide area network over sockets, which is less performance solutions, but still available. One caveat, though, is that the MPI transport layer for the SSD engine, unfortunately, is currently not working on Aurora due to some issues initializing MPI, since you need threading support, but that is something that we're working on and expect to have fixed in the future. And then to keep in mind is that Adios 2 supports this, what's called the M to N model, which means that the producer and consumer ranks don't have to match. And so in this diagram down below, you can think of, again, a producer. This could be a simulation running on M ranks on your system. And then the consumer could be either co-located or clustered in terms of its deployment, but it can really use an arbitrary number of ranks. And so what is this SSD engine really helpful for? What should we think of? How do we think about using it? So I would say the best types of workflows or applications where this can help is the cases where there's a single producer. And also fairly important is unidirectional data flow, as the diagram shows. You can do bidirectional data flow with SSD, but it becomes a bit more cumbersome. Also, I would say in cases where you have lower data reuse, so you don't need to produce a lot of data and then reuse it, say, from the consumer side, as you may do with training, you can basically, as you stream the data, store it somewhere, but then it's up to the user to implement some additional code to do that. SSD with Adios really just gives you the streaming functionality. But it is a fast and scalable data transfer, as you'll see in a second. And so if performance over the interconnect is what you need, then this is a good option. Another thing to mention is this idea of synchronous and asynchronous mode with SSD. So there's a bit of a code snippet here, just to give you an idea of how you would set that up. But really, there's two ways you can run, in my opinion, or two main ways in which you can run SSD. In the synchronous mode, you effectively are, even though you may be, the components may be running on different hardware, you still can force a sequential execution of the workflow. Effectively, by setting some of these parameters, you can force the producer to wait for the consumer to even be ready to receive data and open the stream. And then you can block the consumer if more than one step is in the queue. What that means is effectively that the producer is waiting until a queue, the queue is freed by the consumer. So in this ways, you can, again, force the sequential execution, but it does increase idle time quite a bit on the producer side if you have a slow consumer, which again, may be what you want, but something to think about in case you don't. The async mode, though, gets around this issue. And so this really allows effectively the producer to keep making progress, regardless of whether the consumer is ready or not to receive any data. One thing to keep in mind, though, is that there is still this queue limit policy here, or this queue limit parameter. What that means is that the producer is then discarding some steps to send for streaming after the queue reaches that limit. And so you're effectively, in some ways, forcing the producer to discard data if you have a slow consumer. You can also set this queue limit to 0, which means that the producer never discards any data, but then you're then accumulating and effectively staging a lot of data on the producer side, which you may not be able to free up on the consumer side in case that's low. Another thing to keep in mind, which we see is very helpful, is this using this open timeout second parameter. In case the producer and consumer take different times to open their streams and synchronize, that can be really helpful. Now, with ADIOS2, we really wanted to look at performance, and so we can think of a simple example where we have a single producer and a single consumer in a clustered case, so that we force communication across the interconnect. And so in this diagram here, you see that effectively we have two nodes, and we have the same number of ranks on the producer and consumer side, each sending data of increasing size over the interconnect from the producer to the consumer. So effectively here, our target or our benchmark is an equivalent setup, an equivalent workflow, but just simply written with MPI send receive. So you can see that for the one rank case, so this is one rank per node on two nodes on the left, the MPI benchmark actually gets really close to the NIC bandwidth on Aurora of 25 gigabytes per second. So that's sort of our top performance benchmark. But with ADIOS2, the RDMA solution and the WN solution, the wide area network, or really TCP IP communication, are not performing quite as well. As we go from sort of all the way from a few kilobytes to 4 gigabytes. But one thing to note, as I mentioned again, is that unfortunately the MPI transport for ADIOS2 is not available due to some issues with how ADIOS2 is being built with MPI on Aurora. And so we do expect eventually to get the same performance as we can with the MPI benchmark. If we scale up, effectively go from 1 to 12 ranks per node on Aurora, we see that we still get pretty good performance for the RDMA transport layer, but instead the wide area network or TCP communication does not scale up well in this case. And this is because for both MPI and for RDMA with ADIOS2, we were really able to utilize all of the 8 NICs on the Aurora node in this case. We see that there's 12 ranks per node and 8 NICs, so there's a bit of contention. So even the MPI benchmark doesn't quite get to that 25 gigabyte per second, but we can still saturate the network with the MPI, and RDMA can also saturate with some larger message sizes. And then this was just a 2-node example, but how does then this scale up to 1,000 node? And so here we fix the data size. In this case, we're just under 1 gigabyte per rank with a 12 ranks per node case. And then we just effectively perform weak scaling up to 1,000 node. And again, you can see the MPI benchmark scales quite well and is fairly close to that ideal scaling line. But also ADIOS2 RDMA proves to be a very scalable solution. And keep in mind that at at the 1,000 node mark, we are effectively moving 5 terabytes of total data between the producer and consumer. And so SSD streaming with RDMA can be really a scalable solution on our systems. And as I mentioned earlier, we do expect similar performance to the MPI send receive benchmark once we address that MPI transport engine issue. And so SSD can be a very scalable solution for this streaming pattern. But ADIOS2 is also traditionally used for I/O to the disk. And so another way of coupling simulation and AI, right, could just be to use the Lustre file system. So again, on Aurora, we were able to benchmark performance with this same sort of single producer, single consumer example. So what you can see here is same plot in terms of rescaling, but we've added a couple data points for Lustre with and without striping. And so as you can see, for some of the higher node cases, we increased the striping count to 8 and then 16. So you can see that the streaming solution is significantly more performant than the Lustre I/O. This is, again, one of the motivations as to why you may want to couple simulation and AI with some of these workflow tools and do things online or in transit, is because you can really get that increased data transfer performance that you would otherwise have if you had to use Lustre. Keep in mind, though, that it is, even for Lustre, fairly good performance. We can get close to 200 gigabytes per second with a 650 gigabyte per second max bandwidth for Lustre, especially when we increase the striping count. But what I think is particularly interesting on Aurora, and something that we encourage our users to try out, is actually still doing I/O with something like Adios 2, but instead leveraging Deos rather than Lustre for the data staging. And so in this case, we performed some tests, effectively the same. It was the same case as using Lustre, but we used a Deos POSIX container instead. And here you can see with the pink line that we can actually get quite good performance, getting somewhat close to the streaming solution. And so this was really encouraging because Deos, I think, could be a great solution for these workflows to try to combine performance of the data transfer as well as persistent storage of that data. So, what if you want to transfer the data across the components, but you also want to make sure that you store it, say, for training later on, or to access it, for provenance reasons. And so Deos, I think, can be really a significant or a very performance solution on Aurora for some of these workflows. Maybe I can stop here for a little bit. If not, the other tool we wanted to talk about, which we've been supporting at our facility for a while, is called SmartSim. And this is an open source tool developed by HPE that was sort of intentionally designed to solve this problem of integrating traditional HPC simulation with machine learning. It comes with two libraries. SmartSim, or also called the infrastructure library, is effectively a series of Python APIs that users can use to manage and build their workflows, which include launching HPC applications across the nodes. And so with this infrastructure library, these Python APIs, you can effectively build your driver script, which manages the components and then also gives you the fine-grained control over where the components run. One of the key pieces of SmartSim, though, is that it currently uses an in-memory Redis database for their staging and sharing data across the components. And you can see that on the diagram on the right. So the database is at the center, as I think about it, of a SmartSim workflow. And SmartRedis is the complementary library to SmartSim, which is really just the client APIs that allows the components to attach and communicate to the database. There's support for Python, C++, and Fortran. And this allows for easy data management as well as some model inferencing capabilities as well. And then another way to think about it of SmartSim is really the whole hub and spoke model, as you see on the diagram. And so this is really ideal compared to Adios 2, in my opinion, for complex workflows that have multiple producers, multiple consumers, and especially that these consumer or these components are both producers and consumers of data, depending on their needs. So you can see from these arrows in the workflow that there's really no sort of unidirectional data flow. Really, the data can flow to and from any of these components. Because of the database that allows data staging, I think this is also particularly useful for cases where data reuse or long-term staging are important. So for example, in the case of training, you may want to accumulate the data that the simulations are producing so that you can keep training on all the data that's being produced. And so this database really allows an easy solution to keep accumulating that data. The other thing that I think SmartSim is very helpful for is if you need user interactivity or dynamism. It is very easy to, even after the workflow has started, to attach components to the database. And so effectively, as you can see in the diagram, this is how I see an easy way for the human in the loop to connect to the workflow. You can attach to the database and then effectively communicate to all your components through the database, or be able to query the data that's being produced or models that are being produced as you're performing training, or even you can perform inference on some additional data that you may want to bring to the workflow. So that's, I think, a key part of SmartSim. And again, please see our documentation for instructions on how to build these on our systems. Something that we've been trying to work on with SmartSim is really sort of benchmark the co-located versus clustered approach. This idea of data staging is very powerful for online training workflows. But how do we think about scaling these workflows to thousands of nodes where both the data producing simulation and the trainer need to scale to thousands of nodes as well to tackle really large problems? And so one way to do this is through collocated deployment, which, as we mentioned earlier, it means that your components are sharing the resources on the same node. And this diagram shows effectively both simulation and machine learning using GPUs, but that's not necessarily the case. With SmartSim, you do have that fine-grained control that I mentioned so that you can really decide if you're wanting to use the CPUs or the GPUs on the nodes for each of these components. But this collocated deployment, again, as I mentioned earlier, really removes all internode communication for these data transfers across components. In the clustered case, instead, you do have that internode communication, which in the case of SmartSim is done through TCP/IP, and so it's not perhaps as performant as we saw earlier with Adios 2 and streaming through RDMA. And that becomes especially apparent with, again, sort of this single minimal reproducer example that we can produce with some of these workflow tools, which for the case of co-located is effectively 2 nodes of this diagram here. And then for the case of clustered is exactly this diagram here, where the database, the consumer or ML component, and then the simulation producer are all on separate nodes. So you can see with SmartSim, both co-located and clustered solution, we're not getting quite as much performance as we did with streaming through RDMA with Adios 2. Especially as we go to more ranks per node, we can see that the performance drops with SmartSim. This is because we're not really leveraging all of the NICs that we have available on Aurora. And so there is contention. And then the extra step to keep in mind here is that the Redis database is taking in the requests from the producer and consumer in a sequential fashion. And so there's also some contention in terms of handling the requests from multiple ranks versus a single rank. But I think what's perhaps more important with SmartSim is how do we think about scaling these workflows? Again, how do we support online training from really large simulations, which need thousands of nodes to run on and produce large amounts of data? So again, with the single producer and consumer example, we performed weak scaling, in this case on Polaris, up to effectively the full size of the machine. This was 448 nodes with 4 ranks per node. And what you can see on the left is the average time for the send and receive pieces of the workflow. So how much time the producer is spending sending data to the database, and how much time the consumer how much time the consumer is spending receiving the data. And so you can see that regardless of the number of simulation ranks, which scale linearly with the number of nodes, we really get effectively ideal scaling. This is because, as the diagram showed earlier, we can eliminate all of that internode communication. So this co-located deployment of SmartSim is really what we suggest for workflows that need that scalability and can benefit from the data being effectively divided among all the different nodes that the workflow is running on. If instead a centralized location where all the data is needed, then we have this cluster deployment. In this case, though, we see that the time spent doing send and receives is growing quite rapidly as the number of simulation ranks increases. As I mentioned, this is mainly due to the number of requests from the simulation and or the producer and consumer clients increasing. And so you can see that we can actually mitigate that and still achieve effectively a flat scaling curve if instead we increase the size of the database linearly with the number of clients as well. And so, for example, if we go left to right on this diagram, you can see that if we go from 1 database nodes to 16 database nodes, we can effectively keep the time of those send receive operations flat. And so that's true sort of for different number of clients as well. So the cluster deployment can be made to scale as well by increasing effectively the database size in order to handle the increased number of requests. So I wanted to move on to the next tool, which is Dragon HPC. And here, the way that we think of it is in a way similar to SmartSim. It does allow for that data staging component, but perhaps it's ideally suited for Python workflows. And this is because it's one of the main features that Dragon HPC provides is effectively a multi-node version of Python multiprocesses. So if you're familiar with Python multiprocessing, for example, MP process, MP pool, MP queue, what Dragon HPC allows you to do is effectively scale that up to multi-node effectively, though without any changes to your code. So that's one of their key features. But they also provide, again, from the Python side, this is very convenient, but they provide effectively a distributed shared dictionary, which they call a distributed dictionary, which has both Python and C++ clients. But from the Python side, it is really convenient because you use it just as a simple Python dictionary. But Dragon also then allows for parallel process launching, including PMI-enabled process launching for MPI applications, again, with that fine-grained control of where each of the processes will run on your hardware. Over SmartSim, though, it does provide an advantage in the sense that it does support RDMA transport agents for that internode communication. And so thinking of these co-located or really the clustered types of workflows that I described earlier for SmartSim, we can effectively get a boost in performance over SmartSim by using Dragon HPC and their RDMA transport agent. And another interesting feature that I won't touch on today, but they do allow visualization of telemetry data, which could be hardware utilization metrics, for example, but also custom performance metrics. And so Dragon HPC, in effect, does allow you to get a live view of how different components of your workflow are performing. So with sort of this initial description, I would say Dragon is really ideal for extending Python workflows from local machines to HPC clusters. In some cases, you can actually do that with just a couple lines of code, changing just a couple lines of code. It is still very adequate for complex workflows like SmartSim with multiple producers or consumers because of this distributed dictionary. And so similarly, it can provide support for the data reuse or long-term staging. But as I mentioned, it does, I think, maybe have a leg up over SmartSim in some cases in the sense that it can provide that RDMA transport across the different components or to and from this distributed dictionary. So going back to that minimal reproducer example, this case is set up very similarly to how the SmartSim example was set up. And here with the purple and brown curves, you can see that, especially for the 12 ranks per node case, we are effectively getting the same performance as we were with Adios SST. So here we can get a significant gain above SmartSim and be competitive with a streaming solution like Adios SST is. But because of, I think, its uniqueness of extending Python for HPC, I did want to spend some time talking about some tests and cases that we've run with Dragon HPC on Aurora, specifically intended to test this effectively multi-node Python multiprocessing support that they have. So for example, one case we did is we try to do distributed data loading of large data sets, specifically data sets that were divided into a large number of files. And we were doing that with multi-node pools effectively, and then storing that data into their distributed dictionary. So you can see on the left with some strong scaling tests that as we go from a few nodes to on the scale in this case of hundreds of nodes, that we can get significant performance up to the point where then the task per pool worker become too light. But even for the full data set, which is 6 terabytes big, but more importantly, it's effectively 500,000 files that we were loading. And so you can see that for this green curve, we were loading that in just over just under 2 minutes on Aurora. And then another thing to keep in mind is that the distributed dictionary does allow for effectively under the hood, they deal with using a hashing function. They do load balancing of all the data that is being added to the dictionary. And again, this is this idea that you can effectively access the distributed dictionary just like a simple Python dictionary, but under the hood, the data is being distributed across all the nodes across which the dictionary is deployed. And so we try to measure the memory imbalance here with these red curves. And for the large data set, the full data set, you can see that we're below the 10% load imbalance, even at the highest load count for node count for this case of 250 nodes. And then thinking about how to use Argonne HPC for sort of more complex workflows, we did some tests again on Aurora on scaling. In this case, it was a fine-tuning workflow for AI surrogates for drug discovery. So just at a high level, the workflow was composed of a few steps. First, we need to screen these large list of compounds with an AI surrogate. We then would sort the top candidates based on the docking score, which is sort of a measure of how likely the compound is to bind to a target protein. We would then perform some simulations on those top list of candidates that were identified from the screening, and then use that new simulation data to fine-tune the model. And then this loop would repeat. And this was all in Python because the docking simulation component was in Python as well. But with Dragon HPC, we were really able to stagger all the components together and utilize multiple of these distributed dictionaries to really ensure that we had concurrent operation as well as really co-location of data and compute. So again, in this little diagram at the bottom, you can see, for example, that there's a top candidate dictionary that spans all the nodes. This is because this is needed by effectively all the components. But the inference data dictionary is only located on the nodes performing inference. And so here we were really able to effectively maximize the I/O or the data transfer time that inference was needing to get new compounds just to screen through them and minimize the communication across nodes. And so when we scaled this entire workflow on Aurora, what we were able to show is effectively really good scaling of all of these components. And so on the right here, you can see that there's the data loading piece, which is actually is the slide before that I showed, which we were able to scale effectively perfectly with that and that multiprocessing pool across nodes. We also have inferencing, which again was able to scale perfectly, but also sorting and simulation, which are slightly different tasks. In the case of simulation, it's actually a strong scaling performance plot. But again, we were able to effectively, by using these dictionaries and the Dragon native process launching, really able to optimize in how we were deploying and scaling up this workflow on Aurora. And this was all the way up to 544 nodes. And so finally, the last thing I wanted to mention, which is perhaps a bit trivial, but worth mentioning, is that we talked a lot about co-location of data, right? And so for a lot of cases, we can leverage these workflow tools that allow us to sort of have a wrapper around process launching, as well as a wrapper around staging the data for the duration of the run. But of course, a sort of traditional solution is to use no local storage for some of these co-located workflows. So on Aurora, that would be only the DRAM is available through temp, but on Polaris, you can make use of actually a pair of 1.6 terabyte SSDs through local scratch or DRAM. And so this is really perhaps the more bare bones, but in some cases, ideal solution if really what you're after is really fast I/O. I would say especially for small data sizes. So here's a diagram comparing Redis, which is effectively the backbone of SmartSim, the file system, Lustre on Aurora, Dragon HPC, and then the no local solution. So this would be DRAM on Aurora. And you can see that for small message sizes, below a megabyte even, really the no local solution is the more performant option. As you go to larger message sizes, that's not necessarily true anymore, but that's definitely an option to keep in mind for our users. It also would, in a way, keep the workflow simpler. You don't have to learn a new workflow tool. Yeah, I did want to mention that as an option. We are seeing that co-located solutions can benefit from going straight to temp without needing perhaps the complexities of a workflow tool around it. So in terms of summarizing what I've talked about today, um, I think the main points are that coupling AI with traditional HPC simulation can be beneficial for your science campaigns, but the deployment and how to actually integrate all the components together can still be a bit challenging. There's a lot of things to consider if we really want to get good performance and good scalability on HPC systems. And at ALCF, our users can leverage various approaches that we talked about today. There's various software tools that we are supporting. And so what we would suggest is sort of based on some of the information that we talked about today, but also reach out to us and we can try to work together to see which of these approaches would work best for your needs. But also keep in mind that you can bring your own tools on our systems. And of course, we will try to get those working and support for those as well. So something that I wanted to end with is perhaps also a user guide on how do I at least think about implementing workflows that try to do simulation and AI together. And so this is not an exhaustive list of questions, but perhaps some of the more important ones that we also covered today. I would say if you need fast inference, then tight coupling with direct memory access through something like the PyTorch C++ library is really your best option here. If you need, or if you're okay with unidirectional data flow between, say, a large-scale producer and a large-scale consumer or a few consumers, then streaming with Adios 2 is also your best option, especially because of their RDMA transport, but in the future through their MPI transport layer as well. If instead you need to combine data sharing, so you're trying to transport data across components, but you're also looking for persistent storage, so you're effectively trying to do both, in quote, streaming as well as storage on the disk, then really on Aurora, we suggest leveraging Deos, as we were able to show it has really good performance at large scale as well. For complex multi-component workflows with many producers, consumers, data flowing in really any direction you want, we would really suggest SmartSim and Dragon HPC. Again, if you're trying to stage large data sets that need to be distributed across many nodes and reuse data throughout the workflow, we would also suggest SmartSim and Dragon as well. And then finally, something I didn't touch on today, but it is on our documentation is what if you need specifically integration with large language models? And so for that, it's something I didn't talk about today, but we do have an inference endpoint at ALCF where users can interact and send requests to large language models that we are serving on our systems, both from login nodes and compute nodes. And so this would allow integration not just with maybe more traditional AI for science models, but also with large language models and start to build some agentic workflows. And maybe the last message I wanted to close on is what are some best practices? How do we think about sort of putting the components together or some of the things sort of before we even get started? So the first thing I would say is to really try to limit I/O to the parallel file system by either streaming data across components or trying to stage them in some way. With the caveat, though, that remember that Deos on Aurora can be a very performant solution. So we do invite users to try that out if they're interested. The other one is to try to ensure high data reuse. And this is really obtained by staging the relevant data that you need in memory. And again, we talked about solutions for that. Finally, really try to ensure good resource utilization by leveraging all the CPUs and GPUs. And so here we get back to the idea of co-located deployment and really trying to exploit concurrency of tasks when possible. And so that fine-tuning workflow that I showed earlier is a good example of multiple data staging solutions and multiple compute components working together to try to really optimize this co-location of data and compute. One thing also I will point out is make use of CPUs on Aurora. This is especially true there. There's a lot of CPUs. These are quite powerful. And we're seeing a lot of workflows are really benefiting from this idea of concurrency, but offloading some of their, or bringing back some of their tasks away from the GPUs and actually using all the CPUs available. And finally, for good scalability, really the key, again, maybe with HPC in general, is reducing your data transfer across network. So again, here, co-location of data and compute is the keyword, or perhaps fast streaming solutions with RDMA and MPI. So with that, I wanted to close and open it up for questions, and thank you for listening. And if you have any more questions or want to discuss, please contact us at our support email, support@alcf.nl.gov, and finally acknowledge that funding for this work comes from the ALCF Computing Facility.